this video, we're going to be continuing with our AP Physics 1 lecture. We're going to delve into vector addition, which is the first part of this video, and then we're going to delve deeper into advanced projectiles. Now, vector addition, the main takeaway is that you're primarily going to be talking about trigonometry, and it just prioritizes your trigonometry skills, basically. Whereas advanced projectiles is actually not as advanced as you think, and that just requires heavy algebra. So let's do vector addition. So let's say we have this triangle, and let's say person A, so let's write A here, is going 32 meters at, say, 15 degrees west of south. And as for person B, let's say they're going in a completely different direction. Let's say they travel 50 meters and they're going 40 degrees south of east. Now, what you're being asked here basically is to calculate the resultant and the resultant angle. These are the two things that we're basically trying to figure out here. And to solve this is quite a systematic process, so let me go through it. All right, so we can first infer that we have, oh, don't tell me this died again. Oh no. Okay, I'm gonna do this with my finger. So we can infer that we have a right triangle there. We have a of x here and a of y here. Now notice that a of y and a of x are negative because they're going in south and west directions. As discussed in AP Physics before, west and south are perceived as negative. So they're in negative directions. Let me charge my pen so I can use it later. Okay. And as for B, kind of the same thing with B here. By is negative, but B of x is going to be positive because it's going in the east direction. And if you're familiar with trigonometry, you can kind of see where this is going. There's a right triangle here. A right angle, sorry. If I call it right triangle. A of y is our opposite side of the triangle, right? And A, which is 32 meters, is our hypotenuse. We already know it's our hypotenuse because you can see that it connects our theta with the other angle that isn't the right angle. So AY is our adjacent, actually. Sorry, I said opposite, I think. So you'd want to do negative 32 cosine 15. And for A of x is our opposite because it's opposite of our angle. Negative 32 sine 15. And then for for the bx and by values, you're basically doing the same thing, except bx is the adjacent because it's connecting theta and the right angle. So you would do 50 cosine 40, and negative by would be 50 sine negative 50 sine 40. And the reason why they're negative is because, as discussed, they are indicative of reaction. Let's see if my pen wants to work now. Please do. Okay, now you want to... Oh, it actually kind of works. For a while at least. So, now we want to add these resultant values. So we have a of x and a of y here. And then we want to add them with the b values, b of x and b of y. I think my pen's about to die again, but it's fine. You add these together. At this point, you can just plug them into your calculator. I know I'm going to. You don't even need to conduct 32 cosine 15 and then add the other value. You can just type in negative 32 cosine 15, or no, negative 32 sine 15, and then you're going to add that with 50 cosine 40. And then for your resultant x value, you would get 30. And then for your resultant y, you would have negative 32 cosine 15 plus negative 50 sine 40. That would give you, I'm just going to round it to the nearest whole number for now, negative 63. And by the way, your negative values are indicative of reaction, not it actually being negative. So just keep that in mind. So I'm going to go ahead and erase these values because we don't need them anymore. Okay. Erase these. And now what we want to do is we have our resultant x and resultant y values, but we're being asked to solve for our overall resultant and the angle. So there's a way to solve for the resultant and a way to resolve for the angle. There's two different ways. We're going to first solve for the resultant value. And the way to do that is with this simple formula. All right. You can pretty much just plug these in. We already know what r of x and r of y equal. You would have to do square root, parentheses 30 squared, plus parentheses negative 63 squared. And that would get you 69. Funny number. 0.78 meters. That's your R value. Now we need to figure out the overall angle. And the way to do that is with tangent inverse R of y over R of x. By the way, if you don't know how to do tangent inverse on your calculator, if you're using a TI-30XS, you would want to hit the light green second button at the top left of your calculator, and then hit the tangent button. And that will give you tangent inverse. So let's plug this in. So tangent inverse, and then you're gonna put in negative 63, 30, and then you would end up with this weird answer. And the reason this is weird is because you don't usually have negative angles in regular math. But this is your angle for this problem. What this basically means is that the angle is going to be south or west of something rather than north or east of something. So let me show you what this means. So going back to the original problem, we're first going this way, 15 degrees west to south, and we're going this way, 40 degrees 40 degrees south of east. This is where you initially started. Imagine we have our little XY plane here, and this is basically where you're going. And your angle would be around here. And this represents 64 degrees south of east. That's how you can kind of comprehend it. Okay. That's how you solve for, oh no, I erased the title. That's how you solve for your resultant and resultant angle values. Now let's move on to projectiles. And let me retype this just because it doesn't look as good. Okay, now let's move on to advanced projectiles. And what advanced means is that basically you have two situations. Oh no. Wait, oh, it's because we have this. Okay, thought my pen died again. We have two situations, right? Normally we have that situation where we're on flat ground, flat surface. We start from the flat surface and end at the flat surface. That's not what we're going to be doing here. Instead, we're going to have two situations. We're either going to start at the top, work our way to the bottom, or we're going to start at the bottom and end at the top. And there's going to be displacement here, displacement here. Let's go over this method first, and then we'll move on to this method. I don't want to erase the title again. All right. Let's say we have this situation, and we are, say, 400 meters above the ground, right? And we throw a ball, and it reaches the bottom. And we initially throw the ball at, say, this is going to be really unrealistic, but 300 meters per second. We already know we have this, VIY, Vx, our angle, our right angle. Our angle, let's just say, is, why not, 30 degrees. Here's our Y max. The time down. Unlike in the previous situations, the time down and time up are not equal to each other. Because we're not starting from a flat surface and ending at the flat surface. There we have our displacement. Now let's say we're trying to figure out our displacement, like anything else. So let me go ahead and erase all this, just to simplify this a little bit more. And the steps, oh, I erased the title again. Oh well. And the steps that to this question is actually pretty much the same as you would do in a normal projectiles problem. There's just one teeny tiny difference that you have to make in the fourth-ish step. So we have this. Let's work our way through this slowly. VIY is the opposite, and we are 300 meters squared. 300 meters, 300 sine 30, V of x, 300 cosine 30. We can honestly just save V of x for the end, because V of x doesn't change, and we won't need V of x till the end, yeah? So let's not solve for that just yet. Instead, we can solve for VIY because we do need that. So 300 sine 30, and that will give you a perfect 150 meters per second. And just like in the how you normally do it, your first step is to solve for TU, the time that it was up. And you would end up with the equation of this. This is the the happy face equation because it's the easiest equation. And note that VFY is equal to 0 because when we're at our maximum height, our final velocity in the y direction, or our y velocity, is going to be 0 because we won't be moving up or down in that instant. And our acceleration due to gravity is always going to be 9.8. It's a terrible looking 8. I'm sorry, I'm kind of messing up today. Okay, so let's rearrange this equation. Like I said before, minus VIY on both sides. We're trying to isolate TU and divide AG, and you end up with this equation: TU equals VFY minus VIY divided by AG. We already know our values, we can just plug them in. We have negative 150 divided by 9.8. And it doesn't really matter if you get a negative value for your time because time just cannot be negative, at least in this case. So let's just say we have 15.3 for our time. For our time up. Let's go ahead and write that down actually. I should actually write all of these values down, just so we don't forget. VIY equals 150 meters per second. Okay. Now our next step is to figure out the Y max. So, to figure out the Y max, like I said, delta Y, or I guess in this case, just to not overcomplicate things, Y max equals, if you look at your kinematics equation, VI Y TU plus 1/2 AG TU squared. And before you tell me that these variables look very confusing, they're really not. What these little subscripts are telling you is what kind of velocity it is, what kind of time it is, what kind of acceleration, and what kind of displacement. Yeah? This is the y max. This is the initial velocity in the y direction, the time up, and the acceleration due to gravity. Okay. Now I want to figure out y max, and we already have our values because we know what VIY is, we know what TU is, we just solved for that, and acceleration is just self-explanatory. So you can all plug these in the calculator, and 1/2 times 9.8, or negative 9.8. I think I forgot to put the negative in 9.8 the last time, so I'm sorry about that. 9.8 is supposed to be negative in all these cases, except for forces. And we end up with this. Y max equals 1,147.959, or you could just say 1.148 kilometers. But I think you can just say 1,148, just to stay safe here. And that would be your Y max. So we know what Y max is. Let me just go ahead and write that down. And I think for my Y displacement before, I said 400 meters. So let's go ahead and write that down as well. All right, now this is when we need our displacement to kick in. So let me explain why we need our displacement all of a sudden. So you have this situation. Start over here, 400 meters above the ground. And we're currently we've solved up to here at the y max. This is the y max. Now notice that the time up is going to be less than the time down. And the reason why is because the length of the time up here, see this length? This is the time up versus the time down. Look how big that is. So there's a big difference between the two. And that's what's going to make the time down bigger than the time up. And we're going to be, hold on. What we're going to be doing here in this situation, as I discussed before, we're going to add the y max with the y displacement, which is right here. Ooh, y is in red. Y displacement. So when you add these together, you get 1,548 meters. That's your total y for now. So you can just say for now delta y final. This can be initial. I guess you could call it that if you want. Doesn't really matter what you call it, as long as you know which one you're talking about. Okay, and for the time down, what you would have to do, let me go ahead and erase this part because we've already discussed this. So let's erase this diagram. And you would have to use this equation again, the position function. And I know a lot of you don't like the position function. This is what we end up with. By the way, since we're talking about the time down now, VFY that we discussed before is now VIY. So basically it's 0. And since it's 0, we can just exclude this entire portion. That entire portion is out. So now we just have delta y equals 1/2 AG TD squared. And now we have to isolate TD because we need to solve for that. So we can just divide everything here. Plug it into here, square root both sides. You would end up with this. And you could just plug in the numbers at that point. Oh, delta y final, for those of you that were wondering. So 1,548 divided by 1/2 of negative 9.8. Oh, maybe don't put the negative in, since we're talking about time, so it wouldn't matter too much. I gotta retype this now. Okay. And we would end up with 17.78 seconds. It's actually not as long as I thought it would be. Or not so much longer than I thought it would be. So we can just put this here. Alright. Now our final step is to find delta x in this entire problem. Okay? So, to find delta x, we need v of x and t total. Well, t total we can just get from here. We can just add our times together because we have them now. 33.1 seconds, if you round it to the nearest tenth. And then for v of x, we can just do, I think we had 300. And then it would be cosine 30. You would end up with 259.8 meters per second. Plug these in, 259.8 times 33.1, you would end up with a total of 8,599.38 meters. And that is your final answer. Now, for the sake of time, I'm not going to go over, well, I am going to go over, but I'm not going to go over in too much detail about the next scenario, which is this, in which you would have to use subtraction. And I don't need to go over it too much because it's actually not so it's just not too different from what we were doing initially. So remember how we would add the y max with the initial y displacement in this type of situation, which we were just solving for? Well, in this type of situation, you're gonna want to do y max minus delta y initial, and then you would get by doing this, you would get delta yf, and then you would basically just do everything we did. Everything we just did, you would just put into here. This is equal to 0. And then you just rearrange the equation algebraically, and then you would basically just do everything we just did. The same way. Just a teeny tiny difference. And that is how you solve for vector addition and quote-unquote advanced projectiles. I don't know why I called it advanced projectiles. I just said advanced because I didn't really know what else to call it. Projectiles 2, but that seems too basic, so I just decided to call it advanced projectiles. Anyways, that's all for this video. I think we're done with the kinematics chapter in these tutorial series. So next we're gonna go over forces, specifically force of push, force of friction, force of gravity, normal force, and then we'll move on from there. So that's it for this video. This is probably the last kinematics video, and now we'll move on to forces. So I'll see you guys in the next one.